Okay, so please let's start today in the course in Frontier Research in Astrophysics and Particle Physics of the Master in Particle Physics and Physics of the Cosmos. We have Licia Verde. She is ICREA professor at the Instituto de Ciencias del Cosmos. I don't know which is the official name in English when you translate the
Institute of Cosmoscience.
Cosmoscience, okay. She's a very well-known cosmologist with a long track. Correct me if I'm wrong, she was a graduate in Edinburgh University, also the PhD.
So the graduate was between Edinburgh and Padua,
okay.
And then the PhD was in
Edinburgh. And afterwards, she moved to the US, and among other places, she worked within the WMAC collaboration at the Princeton University for a long period, also at the Pennsylvania University as faculty, and already for more than 10 years you are in Spain, Barcelona, right? So she has a lot of expertise on observational cosmology, both from the point of view of galaxy surveys and of course of the cosmic microwave background. The WMAC team, as you all know, was the one providing amazing results in the early of the 20s, on the zeros of the 20th century, and she was granted together with the WMAP team with the Gruber medal. So you know the mechanism of the seminar. After her presentation, we will have a time for open questions for everyone, and afterward, the students of the Master and all those lecturers of the Master that want to stay with us, we will have another period for a more informal colloquium. Okay. So Licia, thank you very much for coming and accepting the invitation. Please go ahead.
Okay, so thank you for inviting me to be here. It's a pleasure, and I've been instructed to have two velocities, two speeds here, one easier one and one a little bit more challenging one. So depending on how it goes, I may flip some and skip some slides. So I will look at you, and if I see everybody going, then I know. But if I see everybody like this, then I keep going. Okay. So what I want to talk about is not a particular observations or not a particular experiment, but some sort of a little bit of a global view of cosmology, and this is going to be a little bit my biased view of the cosmology. And I entitled this Precision Cosmology Challenges and Opportunities. So cosmology as an extremely successful standard cosmological model. So we are here in the present. The universe has been expanding. It started off with a Big Bang. This we know, even primetime television told us that. And then when we look at the universe, we look back and we look at the distribution of galaxies and cosmic structure. And then since the universe was hot and dense when it was born and it was full of radiation, it comes to a point where we can see directly beyond. It's the surface of last scattering, and it's the very famous cosmic microwave background. So cosmology in the past 20 years has made a transition from what is called precision cosmology, because at the beginning cosmology was the kind of science where you would measure the parameters of your model, or you would measure physical quantity, order of magnitude level. And then there was experimental effort, and then now parameters and physical quantity are measured with percent type of precision, so it's called precision cosmology. And cosmology has moved in these years from a data star science to a data-driven science. And a proof of that is that a lot of people that do PhD and postdoc in cosmology, then they move, if they move to industry, they move into data science for a very good reason, right? So cosmology, as a result of that, has a standard model, and this standard cosmological model needs only a few parameters to describe the origin, composition, and the evolution of the universe at the largest scales. Now we have to keep in mind what scales we are talking about. For cosmologists, galaxies are points. And that's what makes it simple. It makes it simple because electromagnetism, it's both attractive and repulsive, and it's messing things up. Gravity is very, very, very weak. It's much weaker than electromagnetism, right? But gravity is only attractive. So when you go to larger and larger and larger scales, the importance of electromagnetism compared to gravity changes. And so on the largest possible scale, you are basically at first order left with gravity, and gravity is relatively simple. And that's why cosmology on the larger scales becomes simple, even though we want to describe the entire universe. Now, this is not the case in the very early universe, where radiation was really important, right? But there, it was linear physics, it's basic nuclear physics, and that's things that we know, and therefore we can still do precision science at that point. But what I want to go is I want to go a little bit beyond that and say that there is a difference between modeling and understanding. And this implies challenges and opportunities, and this also drives the philosophers of science crazy and really interested about what we do exactly because of this. So never mind that the model is weird. So this standard cosmological model, which is very simple to, very similar to the establishment of the standard model for particle physics, where you have a few parameters and you start putting all the particles in their place and you have an unifying model to describe all the different phenomena. The model is very weird. I'm sure you've heard about that. The universe is dominated by something which we call dark energy. Atomic matter is only 5% of the universe today, and what we see is a very small percentage. There's a lot of matter that we don't see, and it's the dark matter. And then there's other stuff here, photons, neutrinos, and if there are black holes, they're very, which is another wonderful thing that we can talk about, but I'm not going to talk about that, but it's something that is very hot and people are very interested in. So, precision cosmology rely on the standard cosmological model, which is the lambda CDM model. Just 6 numbers describe the universe composition and evolution, and these numbers are divided into 2 classes. There are numbers of parameters that describe an homogeneous background. We know that the universe is not homogeneous, but we describe its background, that's its evolution history, with the famous cosmic pi, called dark matter, dark energy, and normal matter. So here is the parameter, omega baryon for the baryonic matter, omega cold, which is the physical density to the critical density of cold dark matter, lambda for the dark energy, and then we have the present day expansion rate of the universe. We know the universe is expanding, so it has an expansion rate. And this parameter here is a parameter that captures our ignorance of the processes of star formation and galaxy formation that we have to put there to actually interpret the data. And then we have also to describe the perturbations. But no theory of the universe can tell you that galaxy is going to form there and that quasar is going to form there. So we have to have a statistical description. And therefore, it's a statistical description, we have to describe its statistical properties. And all the information that is when we look up in the sky, which not all, but a big part of it, get compressed into something that is called the power spectrum. But all the information about the primordial perturbations that were there get compressed into number, which is the amplitude of a primordial power spectrum. And then we say it's a power law, and the other parameter is the spectrum. Now this leaves questions open. Where the heck is lambda? What the heck is cold dark matter? Particle physicists, if there is an extra particle that makes a cold dark matter, should have found it in their experiment, and yet they haven't. Well, you know, there are the Dama results, but nobody believes the Dama result. There's another discussion that one can have, a side discussion. And about the primordial perturbations, the seeds that gave us the galaxies and the planet and everything that we can see today, then the question is who put them there, or what put them there. So cosmology is special on top of that, because we can't make experiments. So we sell to the funding agency the idea that we make experiments, but we don't. We can only do observations, because we can't poke the universe and see how it responds. So for anything, we have to use the entire universe as a detector, but the detector is given, and we can't tinker with it. So in particle physics, when you do a neutrinos experiment or a dark matter experiment, you build a detector, but you can tweak the detector. Here, the detector is given, just live with it. This has driven a massive experimental effort, that is, observe as much as possible of the observable universe, because you want to be sensitive, you want to make your detector as big as possible. And it is a mixed blessing, as a curse and as a blessing. What is the curse? The curse is that we only have one observable universe. So we can only make observation and only of the observable universe and not experiment. So we fit model. Model fitting means constraining numerical value of parameters to the observation. And therefore, almost any statement that we do in cosmology ends up being model dependent. So there are some statements that are not model dependent. But every time you read a statement in cosmology, ask yourself, is this model dependent or not? And at least 90% of the time, it will be model dependent. And there is also astrophysics, which is not a typo. It means complex astrophysics that is poorly understood or hard to model, and non-linearities gets in the way. Basically because our main messenger to see the universe around us is light. But the light interacts with other things that are out there. Light is emitted by galaxies, and galaxies or quasars or whatever are complicated objects, and that's where the astrophysics come in. And also, non-linearities comes because at the beginning, the primordial perturbations were small, and they were growing linearly, and that we can model and understand very well. But the moment when gravity grows this primordial perturbation and they become large, then they become non-linear, and those non-linearities are very hard to model, and that's why. But this is also a blessing, because if you have only one observable universe, in principle you can observe all there is to observe. And then you can make what I call the ultimate experiment, or the ultimate survey. Since you observe all there is to observe, you made it. You made a service to humanity. It's there. That's all the information that you can never hope to get. It's there. You just have to get it out. So we can observe all there is to see, and actually we almost do. And I give you an example of what is almost. The future is bright because we can make ultimate survey, and we're getting there. The future is here. This is an example of the ultimate experiment. This is the Planck satellite. This is my rendering of the Planck map. You have Planck expert in this room. I'm not part of the Planck collaboration, so I'm just gonna tell my perspective on the importance of this result for the argument that I'm doing. For the experts, ask them. But this is our ultimate experiment. For primary CMB anisotropy. That is, if you want to know about the early universe, anything that set up the initial condition, and then this initial condition then evolve after that, and if you want to look at the temperature of this map, then that's it. That's the ultimate, that you can't get more information out than Planck got. Does it mean the CMB science is finished? Of course not. We know that this radiation is polarized, and there's a lot more information to be gathered than we have done and that Planck has done in polarization. So that's to keep in mind. So, and we were able to extract a lot of information and exactly what propelled cosmology into precision cosmology were observation of the cosmic mechanical background. And your question may be, well, how is that? So let's run quickly through the argument. The universe, back then, when we get this, when this radiation was emitted, was made of a very hot and dense gas, so it was emitting radiation. This is the radiation we see when we look at the cosmic mechanical background. This radiation is uniform, but with a tiny density and temperature ripples, and tiny means 1 part in 100,000, more or less. But if I'm talking about ripple in a gas, I am basically talking about sound waves. The fact that you can hear me talking, it's because my voice is creating ripple in a gas, that is the air. And that's why you can hear me. So that is ripple in a gas. The same kind of physics that describes sounds also describes what we see there. So this is a cosmic symphony. We are seeing sound. And by seeing sounds, you want to interpret what was going on in the baby universe. This tiny fluctuation, quantitatively, not only qualitatively, give rise to galaxy. And I like to make the parallels to what my countryman Fermi was telling people when he was trying to set the funding to see the first particle accelerators. He was saying these particles, which we believe are fundamental, they are not actually fundamental, they are complex. So what we want to do is want to take like two grand pianos, smash them together with an accelerator, and then from the pieces that come out from the wreckage, figure out how the instrument was made. And what I'm saying here is that instead, what cosmologists do, they try to listen to the sound, or actually take a picture of that sound, and figure out how the instrument is made. And this is something that it can be done, because sometimes, if you knock on wood, it sounds differently than if you knocked on metal, or if you knock on some other material. So that's exactly the same thing we're trying to do. And there's another piece of information that you want to have about this. That is, there was a fundamental scale back then, which is how much sound could have traveled given how old was the universe back then. And this is the sound horizon at that time. It's like when you strike a chord of an instrument, or when you blow on a flute or on a pipe. You have a fundamental length, which is either the length of the chord or the length of your pipe. You create sound with it, and you get a fundamental modes and overtones. So in this map, there's one fundamental modes and overtones, and that fundamental modes give you a standard ruler, which is the size of the sound horizon back then. And this standard ruler is fundamental, because we're going to see it over and over again. And thanks to that standard ruler, we were able to learn a lot about both the early and the late universe. Why am I saying also the late universe? Well, because it's a standard ruler back then, but you can't measure distances, right? It's very difficult to measure distances astronomically, but it's very easy to measure angles. So you now have a standard ruler of which you know the distance, you know the length, but you measure the angle is sub-tenth. So you can measure geometry, and you can measure the size of the universe. And that's exactly what this experiment is. All right, so the other information that I want to transmit is that this model, this lambda CDM model, has survived unscathed an avalanche of data. This kind of picture ended up even in the first pages of the newspaper, so you might have seen it already. This is the resolution and the amount of information that was in 1992 with the COBE satellite. This is the WMAP map a decade later, and then on a decade later Planck, and it's two parts of the information. There's both the temperature, so you see how much the resolution increases, but also the polarization of that information. There's a lot of information there, and still the same model has survived unscathed to all this. And so the new lambda CDM model has some parameters, and I'm not going to go through them in detail, but to let you know that the error bars around those parameters are shrinking, and they are very small. So this is the person that gave us the model, which is today is the standard model, and it was recognized earlier, last year by the Nobel Prize, and both for the cosmic microwave background. He was one of the pioneers trying to measure and interpret the cosmic microwave background, and it says for contribution to our understanding of the evolution of the universe and discoveries in physical cosmology. So this is from the early universe side, but also on the later universe side, the same model has survived unscathed an avalanche of data. This was the state of the art in the 90s, where this model was being, formulated completely. And this is something that the poor resolution of my screen and of the projector doesn't do justice of the amount of information we have here. This is taken from the Sloan Digital Sky survey. And this kind of stick man thing would fit in a little corner down there. And also the number density of object is much higher. Each one of these objects, well, this is a pixel. In each pixel there's more than one object. If you see what I mean, it's a galaxy. And this is this survey gives you the three-dimensional positions of millions of objects in the sky. So a maximally boring universe, some people have said that, it's a maximally boring universe. I would say the boring is good, but like the half full and half empty bottle, I'd say that there's never a dull moment, and I'm going to show you why. So, when you do a three-dimensional survey of a map of the universe, you do it by measuring redshift survey. It's called redshift galaxy redshift survey. And it turns out that if you trace year versus log of the number of galaxies, you get this low. And redshift survey are increasing of a factor of 10 every 10 years. Which means that if we extrapolate, and this calculation David Schleger, which is one of the founders and driver of this very large galaxy redshift surveys, all linear modes in the sky will be mapped by 2043, and all detectable galaxies will be mapped by 2061. Golden age or golden rush? We'll have to decide. So my point is, the primary cosmic microwave background temperature information content has been saturated. I weighted my words very carefully, people that are working in the CMB know that. The near future, for me, is large scale structure, which is studying the structure of the universe as mapped by three-dimensional surveys. And the first thing that you do when you get a big survey like slow one and things like that, you compress it into a power spectrum. It's because if you believe that the initial conditions are Gaussian, you know that in a Gaussian field, all the information is included in the power spectrum, especially because the theory is a statistical theory. Now, this is not all the information, of course, there's more information than that, but to first order all the information is in a power spectrum. So what physical information can you extract from these large surveys? Well, from clustering you can ask what are the constituents of matter, what is the physics of inflation, this period of accelerated expansion right after the what's the masses of the neutrino, what's the primordial power spectrum, what's the nature of that matter. Now, from geometry, and I'm going back to the standard ruler in a second, you can ask what's the expansion history of the universe. Can you tell me something about the nature of dark energy? So you see, this standard ruler that I mentioned here, it's tightly related to the standard ruler that we see and measure and was formed in the cosmic microwave background. Because if you have a standard ruler there, that means that the perturbation have a characteristic scale. That is going to be imprinted into the dark matter distribution, and that's going to be then mapped by the galaxy distribution. So the same standard ruler that we've played with in the cosmic microwave background then can be seen in the distribution of galaxies. Again, with a pro and a con. The con is that the amplitude of that particular signal in the large scale structure is much, much smaller. It's of the order of a few percent, while in the cosmic microwave background is a booming signal. But the advantage is that the cosmic microwave background is just a single screen, so you can play that exercise at a given redshift. In the large scale structure, you can do it at many different redshifts, and that really wins you a lot. Now, we measure redshift, we don't measure distances, the universe is clumpy, galaxies attract each other, so there's information about gravity and about physics in there too. So these are called redshift space distortion. So the space distortion could be trash for somebody, but one man trash is another man treasure, right? Could be trash if you measure the redshift and you wanted the distance and you don't get the distance because of this peculiar velocity to the fact that the universe is not uniform. But at the same time is the other man treasure because there is information about the growth of structure and about gravity in there. At the large scale you can ask a question about is the universe homogeneous? Were the initial condition Gaussian or non-Gaussian, which tells me something about the physics of inflation. And then from spectral analysis, because for each of these points, there's a lot more information. This is big data, right? There's like the spectral energy distribution of this object, then you can get more cosmological information, which may be the key to ensure robustness of this. So this means that you can do precision tests of fundamental physics with cosmological data. So the infinitely big meet with the infinitely small. In this Ouroboros, which I think is the technical word for this. So when I hear about concordant cosmology with the standard lambda CDM model, it reminds me of this fresco in Florence, Duomo. Concordance is up here. You have God, everything is happy, everything is in concordance. But then if you look back down, you see that there are monsters and things like that. And, you know, I think that we should look at both sides. And to me, these are systematics, these are possible gaps in the model, these are the difficulty on which the rest sits on. So what kind of fundamental physics can we do then looking at cosmology? Nature of dark matter, nature of dark energy, nature of gravity, physics of the early universe, neutrino mass, etc., etc. So I give you an example, and I will only talk about neutrino mass, but there's a lot more there. So Baryon is good. So what are the challenges? As the statistical errors shrink, the systematic error must be kept under exclusive control. And there is no systematic way to deal with systematic errors. Here it is. So accuracy is the new precision. And how we get there, it's an open challenge. So let me give you some example, and then we can continue in the questions. So the universe, it's permeated by the cosmic neutrino background. These are primordial neutrinos. These are not neutrinos produced in the accelerator as Earth-based neutrino experiments do, but there's a lot of those. This is a relic of the Big Bang, similar to the CMB, except that the cosmic neutrino background decoupled from matter at 2 seconds, not at 380,000 years like this thing. So a decoupling neutrino are still relativistic and have a large velocity dispersion. Now, if you put your thumb out, you have 60 billion neutrinos that come from it every second from the sun. So there's a lot of neutrino here, and there are only about 100 that come from the cosmic neutrino background. So measuring that from here is not that straightforward. They have different energy, that's far enough. But the thing is that the universe is very big, and the sun, the emission from the sun goes down with the 1/r² inverse distance law. So that's why on cosmological scale this becomes important. So what is a neutrino for cosmologists? Neutrino for cosmologists is something that behaves like radiation at early time, eventually possibly become non-relativistics, and then eventually behaves like matter, has a small interaction that is not a perfect fluid, and this is important, and has a high velocity dispersion or is hot. Anything else that does this for a cosmologist is also a neutrino. Okay? But we know that there are at least 3 neutrinos. And so we know that there are at least 3 particles that behave like that. And so we have to put that into the calculation. I'm sure you've seen this picture. This is the Catherine experiment arriving at this place. And this is what I call an ambitious terrestrial experiment. Catherine is supposed to announce results soon. It started about a year ago. So in cosmology instead, what are the physical effects of neutrino mass? So we know neutrinos have mass, because we know there are neutrino oscillations. We've measured the mass differences, but we don't know what is the absolute neutrino mass scale. But cosmology is not sensitive to flavor. Cosmology, however, is sensitive to how much stuff there is in the universe, and is it hot or not? Does it behave like radiation or like matter? And that's what cosmology is. So neutrino of a total mass above 1 eV become non-relativistic before recombination, and that CMB nails it. Total mass below about 1 eV become non-relativistic after recombination, and so it alters matter radiation equality, it alters distances to the last scatterings, but the effect can be cancelled by degeneracies, by other parameters that compensate. However, after recombination, other effects come in, which can be important for the observable that we see after recombination. And in particular, we know that finite neutrino masses suppress the matter power spectrum on scale smaller than the free streaming length. What does it mean? It means that if I'm a neutrino and I have a high velocity dispersion, I will tend to be able to escape from gravitational potential well better than dark matter does. And so if I have mass, as I escape from my gravitational potential well, I carry my mass with me, and therefore I tend to erase the amplitude of perturbation on scales that are below the freezing point. Also, different masses become non-relativistic at slightly different times. So in principle, cosmology can yield some information about the neutrino mass hierarchy, which may be complementary to particle physics experiment. So if you keep fixed, this physical cosmological parameter, omega matter h square, omega baryon h square, which are the physical density and the amount of dark energy, then in linear theory, as you change the mass of the neutrino, the ratio of the linear power spectra will go like this. So the bigger the mass of the neutrino, the bigger suppression you have on small scales. Excellent, we should be able to measure that. I just told you that we can measure the galaxy power spectrum with percent precision. We should be able to see. This is, look, at 0.3 eV, it's 15% effect. It's not that easy. Because you need to move along the CMB degeneracies of the cosmological parameter, not along whichever parameter the direction you want. And then if you do that, this suppression then is not that straightforward. Now, of course, the CMB degeneracy is not one line, and so the reality is somewhere in between. But the important thing is that you start other physical effects start coming in, like suppression of this oscillation, which are called Baryon acoustic oscillation, which I come here a second, will start appearing. And down here is where you see this. So notice that to change on this other set of parameter, I have to play with Hubble. So Hubble is everywhere, and this is going to be important later. So now, in a plot that particle physicists like, this is the mass of the lightest neutrino. This is the sum of the masses. So oscillation experiments tell us that you are living either in this line or in this line, just from neutrino oscillation. This is called the general hierarchy. This is called inverted, and this is called normal. The Catherine, the forecasted detection versus 90% limit will fall somewhere in here. Cosmology, blank, plus some very robust things about large-scale structure, puts you here. This is excluded, and this is allowed. If you add the large-scale structure in a little bit more aggressive way, then you exclude everything else here. And then forecast for forthcoming survey leave down here. So this means that neutrino mass in this range leave a 5% or less effect on the matter power spectrum. But if we are doing precision cosmology, 5% we should be able to see. So cosmology is the key to tell you something about the absolute neutrino mass scale, which other experiments can't or have a very, very hard time to do. However, cosmology is a very indirect measurement and very model-dependent measurement, while this measurement is at least dependent on a different model. Okay? So if we add the latest measurement of the Hubble parameter, then you almost exclude the inverted here. But let's not go there for now. This means that neutrino contribute at least 0.5% of the time. So what are the other implications? This is the effective mass for tritium beta decay. This is the sum of the neutrino masses. Particle physics experiment could cut this way, cosmology cuts this way, and these are the two hierarchies. So it's really complementary. And this is for the neutrino-less double beta decay, sum of neutrino masses again. So cosmology got you here. If you want to get here from this way, you need a ton scale experiment, which people are talking about, but it's futuristic, while cosmology already got you there. You can also say that the inverted hierarchy, poor thing, it's most of it is basically implication. Cosmology is the key to determine neutrino masses. For the pessimist, the inverted hierarchy is under pressure. For the optimist, if it's in an inverted hierarchy, then a measurement of the neutrino mass is just around the corner. I just have to go and do it. So boring is good. However, we can't this quote by Daniel Kahneman. Daniel Kahneman, which was somebody between psychology and economy, saying, we can't live in a state of perpetual doubt, so we make up the best story possible and we live as if the story were true. And in cosmology we have a lot of stories. GR, Big Bang, choice of metric, nuclear synthesis, you name it. They're really model dependent. Cosmology tends to rely very heavily on models, both for the signal and for the noise. Essentially all models are wrong, but some are useful. So I like always to keep this in the back of my mind. But with 1% precision, systematic becomes the name of the game. And systematics can be in the data, systematic can be in the model, systematic can be in the analysis. We cannot take this to life. So what is in the back of my mind is, having saying all that, how do you test the model? And can you do without the model? So the answer to this question, I think, is you can't do without the model completely. But what you can do, you can drop a part of the models and become more model independent and see what that tells you. And so I want to use an example to tell you about that. And my example is what I called the H0 game. Remember, the H0 is the current expansion rate of the universe. And I like this because, to me, it's what I called an end-to-end test. And let me explain what I mean by an end-to-end test. So the traditional way to measure the current expansion rate of the universe is what Hubble was doing at the beginning of the last century. So it was looking for standard candles in a way or another. That will give you an estimate of the distance, luminosity distance. Then measuring redshift, it's relatively easy. You had a distance redshift relation, and then you can get an expansion rate from that. Now, never mind that Hubble underestimated his error and got a value for the Hubble constant that was very far away from what we know the values today. The concept is that. And so we have been doing that for many years on the cosmologists, not me personally, on the footstep of Hubble by building what is called the cosmic distance scale. So you use nearby distance indicator to calibrate the next step of the ladder when you use intermediate distance indicators and so on and so forth. But what has happened over the past 10 years or so is that we have been able to extend this cosmic distance ladder all the way from the local universe to the earliest light and the farthest we can see. So that's why I see this ladder, I draw this ladder that goes from a representation of our galaxy all the way to the early universe and the cosmic microwave. So today, you can have different ways to measure the expansion rate of the universe. The traditional Hubble way, done with parallaxes, cepheids, and nearby roaming. Other method that I'm not going to mention. And then another way, which is saying you take this very earliest light, we know the physics extremely well, we know it's a lambda CDM model. One of the parameters of the lambda CDM model is the Hubble constant. Let me fit this model to this data, constrain the cosmological parameter, and sure enough, Hubble becomes constrained at the 1% level, or even better than that. Now, the big question is, does the number that I get from here coincide with the number that I get from here? And do I get the ladder to actually join? That's why I call it an end-to-end test. Now, given the fact that you have some percent error here, and in the past 5 years, the error on this end also are approaching the 1%, they are at the 2% level. This is like threading a needle from the other side of the universe. So, to understand the step of these ladders, key step of this ladder, let me go back to this BAO, which we've seen appear before. BAO are called Baryon acoustic oscillations. So remember I told you that in the cosmic microwave map, there is a standard length imposed there, which you see as a standard, as an angle, which is this fundamental mode, okay? And this is when you way of actually telling you the physics that goes into the fundamental mode. We don't go there. So here you have photons. Photons are coupled to baryons, so there is that structure there. when you look at a galaxy survey, you see dark matter in the sense that the baryons are tracing the underlying dark matter distribution because of gravity. As baryons are 1/6 of the dark matter, this oscillation that you see here, this standard ruler that you see here, it's imprinted in the dark matter distribution, gravity is the coupling, and then you're supposed to see it from this map of the galaxy. So now you see that standard ruler that was in the cosmic microwave background, now you can see it has several different redshifts, and that's some of the ladder of the step of that ladder. So this is a standard ruler. The cosmic microwave background and early physics in the Lambda CDM model constrained the standard ruler length to 0.2%, and then you observe it, and it's useful for geometry of the universe, dark energy, modification of GR, but also early universe physics, which is well known. But we also have standard candle, like the Nobel Prize on the discovery of dark energy show, it was done with standard candle, which are type 1a supernovae. They measure relative distances because there is a large uncertainty in the absolute magnitude of a fiducial supernova. While baryon acoustic oscillation measure absolute distances, but depend on the value of this standard ruler, on the length of the standard ruler. If you believe you know the length of that standard ruler, then this gives you absolute distances. And the key thing that happened over the past 5 years or so is that baryon acoustic oscillation and supernova start overlapping in the same range of redshift. So that's what allows you to connect the two ladders. So how does it work? The traditional standard ladder is the Deisler cosmic distance ladder. You know, you go from nearby distance indicator to supernovae, but then you stop there if you don't have this. While if you have this, you can go all the way to the cosmic microwave background. Why? Well, because this cosmic distance scale is set by the physics there. You have a direct link. But now you can do an inverse cosmic distance ladder because you have this standard ruler here, which is imprinted there. Now you calibrate these two on one another because they are at the same redshift, and then you go back here. So this is the high redshift anchor, and this is the low redshift anchor. So if you read science, outreach, and so on and so forth, you by now know that the two things don't seem to agree. So two good ladders need two good anchor points, and our two anchor points don't seem to agree. So what happened there? What happened, it goes under the name of the H-0 tension. So I've adapted this slide from Adam Rees, and the problem of this kind of slide is that you need to put a date, but not in terms of year, but in terms of month, day, and time of the day, because things change that rapidly. So since we are not going to be too specialist about that, this plot is like from this summer, but it has changed already from this summer, but it doesn't matter. Also because I don't want you to know all the details of all the various measurements and all the various references. What I will tell you is that these are different measurements of the value of H0, okay? And then different color relies on different technique, relying on different physics. Cosmic microwave background, okay? But this and this don't necessarily rely on cosmic microwave background, right? But rely on the abundance of light element and Big Bang placement. These are direct cosmic distance ladder measurement, parallaxes and Cepheids, and this, again, by now there are 6 lensing with another one that they are unblinding, and the collaboration just made everything public like 2 days ago. But this is based on time delay distance. This is based on gravitational lensing. So completely different physics. And you know, what's the matter here? Well, the matter here is that they don't really agree with each other. And you can put two boxes around, and those that depends on the early universe extrapolated at redshift 0 give you something around 67, while anything that depends on the late universe gives something around 74. And that's never a dull moment. Okay? So my point of view is the following. First, ask yourself, is there a problem? So you need to be quantitative. So there was a workshop this summer at Santa Barbara where all the aspects of the various techniques were invited. Tension ran high there, so at some point I have to put myself physically between two people in order not to violate the code of conduct. But basically, and by the way, this plot and all the data are made publicly available in GitHub, so if you want to do your own version of the plot with the latest result, whatever, just get the code and then everything will be in the same format and you can compare like with like. So the summary, it's between 4 and 6 sigmas, depending on how you do. You need to combine measurement, not each one alone of this measurement with that gives you 6 sigma, but it's between 4 and 6 sigma. And you are allowed to combine different late time measurements if they are different enough and rely on different physics, so you think that the systematics are not in common, and then you can combine. And so that's where you divide. You notice that there is this measurement here, which although it's late time, it seems to be sort of compatible with the early one. And this is the Carnegie Chicago Hubble program. This is based on the tip of the red giant branch. This is where the tensions really run high. And we can talk about it. So I'm not going to say anything about it. So where is the problem? Given that we have a problem. Is it in any specific data set, by keeping the standard lambda CDM context? So for a while, people were putting the blame on Planck. They would say, the Planck is wrong, the early time measurement is wrong. And people that dropped Planck instead still use the cosmic maker background, they still use MAP or MAP plus A plus SPT, etc. But this paper came out, I think in September, which I think it's very interesting. Because the early physics-based H0 measurement does not budge if you take out CMB data completely. Even in model where you allow the number of effective neutrinos to be bigger than 3. One of the initial fix that was proposed was to say, oh, well, you have extra radiation at the beginning. We know we have neutrinos. We know we could have sterile neutrinos. Let's put an extra effective neutrinos and we fixed everything. No, the CMB polarization tells you that you cannot do that. The CMB polarization tells you you have 3 neutrinos. You can't have a 4th neutrinos. But then say, oh, maybe the CMB is wrong. Let's drop the CMB data completely. Let's also allow the number of effective neutrinos to vary. And then this nice paper shows you that by using the abundance of the light elements, we give you an estimate of omega baryon, then your constraint on H0 from early time assumption about physics, you still need to know the BBN happened the way it happened and that the early time history is still the same, is here. This is the CMB result for comparison, and this is the late time result. I mean, this I think is a nail in the coffin for those that say Planck is wrong. There's no way out. Now some people say, aha, but I caught you, because in order to do that, you use the Baryon acoustic oscillation, not only the one observed in galaxies, this is omega mater versus H0, but to break this omega mater H0 degeneracy there, this group added the Lyman alpha. So Lyman alpha is the clustering of intergalactic medium observed by the absorption of the light from distant quasars. Now this measurement is a hard measurement to do. Not everybody agree that the systematics are fully under control, and so the critics say, well, if you drop the Lyman alpha, then you can't say anything. But I say, aha, we have supernovae, and we do believe supernovae. And if I look at supernovae data, let me throw away the Lyman alpha completely. What I need is a measurement of omega mater, right, in a lambda CDM model. And if I look at the supernovae data, the supernovae will tell me that omega mater can only be here. You cannot have omega mater here. And so even if you throw away the Lyman alpha BAO, you still land in the same place. So this is robust. So where is the problem? Is it in any specific data set? All low Redshift determination, except this one, let's talk about it separately, movers above 7. Adam liked to do this tension matrix, which says, depending on how you combine your data set, you get different number of signals. And then he got a prefix menu that goes with this matrix, and depending on what you can choose and what the systematic in common. But you know, the summary is that you have, 4 to 6. So, if not in the data, then is it in the model? And now here we are at the level of this, and this ended up in a pulsing model. So, okay. So what does it mean? So if we replace it in terms of early versus late, it forces you to think of each measurement and what it means. And here is where you can go a little bit model independent. So this was part of the thesis of my PhD student, Jose Luis Bernal, where what he did is say, well, let me allow the expansion history of the universe to be described by S-splines. So this is not lambda CDM. It's not omega matter or anything, just S-spline. And I'll tell the data, supernovae and Baryon acoustic oscillations, to tell me what the expansion history of the universe should be, and therefore able as a function of redshift. And here is the reconstruction you get, and here is what the CMB tells you, and this is the ratio, the lambda CDM one. So basically, you can deviate, but only maximum 5% from a lambda CDM expansion, and that's not sufficient to fix the mismatch. There's no way you can say, I'm going to have some strange dark energy that's changing the shape of this function history to match the two things, because without a model, here I'm telling you, you can deviate maximum 5%, and that's not sufficient. So there was a paper later on by Eilor et al. That again agree with what Jose was saying in his thesis. You can see this as two anchors. So whatever is a problem in H0 is a problem in the sound horizon in the early time. So you could fix that instead of fixing the H0. And that's why they call it sound discordant. Why do I call it sound? So let me go back to this. So model-independent non-parametric analysis, it turns out that if you have H0 and you have the sound horizon, the CMB is here, the large scale structure is here, and the measurement of H0 is here. Now this is my timer of 50 minutes, which means that I have to speed up and conclude, so I may skip some slides. Okay, so, well, you can say, haha, but when you measure the cosmic microwave background, when you measure the sound horizon there, you see the cosmic microwave background through the entire universe, so you have some late time information. Well, it turns out that you can measure the sound horizon radiation, like that's standard ruler, independently of the late time universe. And there's a way to do that, and we did that, and it turns out that the error on this quantity do not degrade compared to the standard analysis. So good. So some work in progress. So in a lambda CDM model, you have H, you have this standard ruler, and this different observation will put lines in here, and that's the H tension, they don't cross. The great success of the lambda CDM and the discovery of lambda is that when we made a plot like this, there were 3 lines and they crossed around lambda 0.7. Here we made the 3 lines, but they don't cross anywhere. So that's why we have a problem. So where is the problem? If not in the data, then it's in the model. Early time measurement assumes standard lambda CDM. They need to assume standard early time history to get you the sound horizon, the standard ruler, while the low redshift measurement would not make assumption about cosmology. So you may want to fix by changing the length of the standard ruler, and then shall we look at pre-recombination or after recombination? Post-recombination, it's very difficult. There are people that have tried, include screening, modify gravity, there are some very creative attempts, but it's very complicated. You would have to affect several different things at once, including time delay distances, which is the lengthening, and that's, that's impossible. People have been very heroic about the effort, but I don't think you can do that. What about pre-recombination? What are the solutions pre-recombination that avoid the constraint that doesn't use the CMB that we've seen from this summer? You can change the sound speed, you can change the initial condition, you can postulate extra component, you can postulate extra interaction among early component, you can change the expansion rate at early time. And there's longer discussion going on. I'm going to skip some slides because it's very technical. But let me just say the pre-recombination solution modify this extremely successful lambda CDM model right there where we most like it. I started this talk by telling you the physics of the early universe is very simple. It's nuclear physics, it's linear, we understand it. It's, you know, the pillar of our entire building of cosmology, and now we're going to modify right there. I mean, it's, yeah. But anyway, if you want to go there, you have to decrease the sound horizon by 7% without breaking havoc on the damping tail and everything else, and that's really a tall order. So some people have tried, and there is a very nice paper by Lloyd Knox and Marius Milea. There's this other paper by Eilor et al. Let me not go there. But the room for maneuver to reduce your standard ruler, it's in the decade or so of expansion of the universe before the combination. You can't do it later because it will not have any effect. You can't do it earlier because it will not have any effect. And if you do there, you can't break anything. So it's very difficult. So it reminds me of fine-tuning. So let me just say that all these options are not equivalent. The next generation of CMB experiment, especially parallelization, will be able to tell you which one of these is, if any, because they will leave signature. So beyond this, that's my question. How old is the universe anyway? Because H0 is related to the age of the universe. So if I plot the same plot, H0 versus the age of the universe, Planck with error bar massively inflated, otherwise you will not be able to see them from the back of the room, sits there. But we can measure the age of the universe. We have old objects there. We've been doing this game since the 90s. So where do we land here? Well, this is part of the Balchin PhD thesis. And let me give you a preview of where we are. So from 38 globular clusters, you get something like this. Okay, this is still work in progress, so let me just conclude. Any theoretical solution should not break out havoc where not needed. So it should preserve the good agreement of lambda CDM with the data, and should improve and not worsen with attention. We should quantify improvement versus predictability, that is the number of degree of freedom that you add to your model, in parallels with lambda. And then we should always bear in mind whether there's model-dependent versus model-independent approaches, and at which point we are adding epicycle. When we talk about epicycle, I like to keep the following in mind. This is a Cassini representation of an Earth-centric solar system. And you see all the amount of epicycle that they have to be added. Now, this is a Copernicus system. The sun is in the middle. This model, however, still had epicycles. It had epicycle because it had spherical orbits, and we know the orbits are elliptical. But there's a fundamental difference between these epicycles and this epicycle. This epicycle says you are on the road of the right solution, but you are missing, you know, a correction there to your model. While this is saying you're completely far away from the solution. So we should always bear in mind when we add epicycle what they mean. So your take-home message is accuracy is the new precision. And when you add epicycle, what does those epicycle actually mean? And I'll stop here. Thank you.
Thank you, Licia. So we have some time for questions before we stay with the students.
Yeah, I have just curiosity. From your point of view, what is the answer? I mean, in which of all these possibilities can be the answer?
Of what question?
I mean, the solution.
So many people ask me that, basically because the two camps have taken such a strong positions. But my position is the following: we should not swipe this under the carpet, which is what was done until basically this summer. You can't just say, no, I don't want to look there, somebody must be wrong. I mean, we are 4 to 6 sigma. If something is wrong, we will learn something very important, either about Cepheids or about supernovae or about physics. But whatever it is, it's important. right? So I think we should look at that, and we should find ways to actually break the problem in a way that it tells you some insight about what physics you have to tinker with and what is your available wiggle room. So in other words, like the way I see it is that all these observations give you guardrails, and then the solution you find needs to fit within those guardrails. But you have to find the solution. You can't just look away and say, no, 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 somebody messed up with the observation. And also you can develop tools, statistical tools or methodological tools that allow you maybe to say who has screwed up with their analysis. The moment you have enough data, the moment you have enough groups trying to measure the same quantity, you should be able to know that. And there are statistical techniques that have been developed in the past 2 years which actually are to be used exactly in this context. So I don't take side, but I think it's really important and I think should be looked into.
Yes.
So you say that eventual solutions to lambda CDM like should not increase other tensions?
Yes.
So what are the other tensions?
So, okay, so there are no other tensions that are as big as this. Everything else is quite concordant. So if you fix this, you should not break what works. If it's time broken, don't fix it, okay? But there is another thing that has attracted attention, which is the tension in sigma 8, that is the overall amplitude of perturbations. What's predicted from the early time universe doesn't seem to match what's measured in the late time universe. However, that tension, it's maybe at the 2.53 sigma, depending who you talk to. So it's something to look at. It's not as bad as the H0 tension, but you can't fix the H0 tension by making the sigma 8 tension 6 sigma. And some of the solution makes the sigma 8 tension 6 sigma. And then, you know, you haven't solved anything. So again, there are some guardrails. Whatever solution you find needs to fit within those guardrails. And those guardrails, given the complexity, well, given how powerful the model is, those guardrails could be somewhere completely else that you haven't looked at.
Maybe I will ask you, because it's related to what you said before. In using H0 as an example of this problem between precision and accuracy, I understand that part of the problem here is we admit that the model is right, that the lambda CDM is right just for a while.
Yes.
Then the problem is in the way in which we understand the observation.
Yes.
So is there any objective manner of weighting our belief on those data points in the sense of how complicated is the physics behind how well we understand it? Because if lambda CDM is right, what it's telling that is some of those error bars are not right.
Either the error bars or the central value.
Yes, but one possibility of hiding everything to a single thing is just keep the central value there, because it's your best estimate, but you have a much larger error bars that is covering that bias.
Yes.
Among those, I don't know if you call it meta statistics,
yes.
That you can do, these kind of things are contemplated in such a way that you put an extra weight or
yes.
penalize
yes.
these kind of things.
Okay, so I have two levels of answer to this question, and it's like approaching the problem from two completely different directions. One is statistical, and one actually, getting into the math of things. Mm-hmm. So the statistical way is basically you add meta parameter when you do this analysis, and your meta parameters tell you how much you trust that observation or how much the central value and the error bar of each observation could change. And then you could actually combine everything, let the meta parameter free, and then ask yourself what the data tell you. You have to be careful of combining only measurements that don't have systematics in common. And in that sense, using the time delay distances with the standard Ceph aids, it's good because they are completely independent. the tip of the red giant branch would also be completely independent, but you can't take, you know, two different Adam Rees papers that have some supernova in common. On the other hand, the maser distances, those are wonderful because basically you're doing parallaxes at cosmological distances. So this is, instead of doing the various steps of the ladder, you just do one step. That can be combined.
That's the point that you were indicating that was a bit more in agreement with the...
No, the point that is in agreement is the tip of the red giant branch, which is a wonderful, I mean, if you go through the physics, it's like, wow, because basically you have it has been described as an astrophysical guillotine. It's when the star through the main sequence in the HR diagram ends their life because they explode and that stop that. So this is beautiful, and that's that point. But that point is not free of other sort of systematics that may come in, but they are completely independent from all the others. So that's, yeah.
Okay. Diego, yes?
Related to the question that Patricia just said, I've noticed that the error bars in the bootstrap estimations are always symmetric. I mean,
yes.
Normally you are using covariance matrices assuming Gaussian distributions.
Yes.
To this point, this is correct or not?
Okay, so in that plot, one of the disclaimers of that plot is we have Gaussianized the error bar. Actually, the full distribution is available from the literature, but for your eye and for a plot, it doesn't really matter. There's no difference, so it doesn't affect the argument. But all the data and all the distribution are public. So. Yeah.
More questions?
One way to deal with this belief in the data, in the sense you trust the data, you are convinced that everything is fine, no systematics, etc. One way to weight this belief may be, for instance, the number of extra parameters that you have to introduce in order to get good results. For instance, for Planck, you know that we have more than 20 parameters, and then we marginalize over most of them except the 6 ones. And this is the same for the galaxy surveys. You also have extra parameters that you don't know how to measure these parameters, and then you assume something and then you marginalize it. So you can think that if you need more extra parameters there, then you don't understand so well the data. So I don't know if this is a way that you think is.
So this is interesting, but it could go both ways, right? Because another way of turning the argument around is to say, look, that's true. I have all this extra nuisance parameter that I need to marginalize. But look, the derivative of the quantity I want to measure with respect to these nuisance parameters is extremely small. And then it tells you that your measurement is really robust. So you can add as many as you want, and you should add as many as you want, but nothing changes. So it can really go either way. But it is a really good argument, right? One could make that argument and then say you can take it whichever way you want, or actually maybe take only those one which the derivative of the quantity you're interested in with respect to those parameters is large, and then if that number is really small, then you can believe it. If that number starts becoming large, then you don't believe it, and that could be your meta parameter that you can use to weight the combination. Yeah, really fun.
Something more? Okay, so thanks again, Licia. So the students now, we break 5-10 minutes, something like that, and then we